Welcome back to your second online lecture for thermochemistry. We've been practicing our calorimetry problems, so we're going to do a little bit more calorimetry today. This is very similar to the type of calorimetry problem that we did in first year chemistry. If you remember, we added a hot metal to cool water, and what we found is that eventually the temperatures equalize. And in first year chemistry, we were looking to find the specific heat of the metal by knowing that the heat lost by the metal equals the heat gained by the water. In AP chemistry, what we're going to do is switch it up a little bit, and what we actually want to be able to do is solve for T final, solve for the TF. So we really need to look back at that equation where it's Q equals M times S times delta T once again. And using this formula and knowing that the heat lost by the metal equals the heat gained by the water, we can see that our Q's are going to be the same. And so what we can do is eliminate Q out of the equation and start using this. The mass times the specific heat times the change in temperature equals the mass, the specific heat, and the change in temperature. One's for the metal, one's for the water. In our search to be able to solve for T final, there is a little bit of a change that we have to make as we come down to the next equation, and I want to make sure you highlight and see the difference here, and it's in the change in temperatures. For the metal side, we want to take the mass times the specific heat, and instead of doing our normal T final minus T initial when we're doing change in temperature, we're going to switch it up, and we're going to do T initial minus T final. This is just for math here, and you really just need to memorize this little switch. On the other side, for the water, it stays the same. We're still doing M times S, and then we're going to be doing T final minus T initial like we've done before. So I have a problem for us to work through solving for T final. A 25-gram sample of copper metal is heated to 100 degrees Celsius, so we're going to heat our metal. And then we're going to put it into a sample of water that's initially at 23 degrees Celsius. One assumption that we're going to make is all the heat that's lost by the metal is absorbed by the water. And what we want to do is calculate T final for this. Notice I gave you the specific heat of copper. Yes, you do know the specific heat of water. That's one of those things that I've asked you to memorize. You had to memorize it last year. And so let me take you through how to solve this problem. Probably the trickiest part about this problem is some of the math. So as I go through the problem, you'll notice that I will make notations of mathematically what I'm doing on each step along the way. Okay, so let's start off with a little bit of given and find, because there's a lot of information in this problem. So we have the copper, and we have our water sample. And for our copper, we know that its mass is 25 grams. We know that it was initially at 100 degrees Celsius. And they gave us a specific heat, which was 0.385 joules per grams degrees Celsius. We also have our water, and we know that we were starting with a mass of 45 grams. Its initial temperature, it was cool, it was 23 degrees Celsius. And the specific heat we always have memorized, which is 4.184 joules per grams degrees Celsius. And we're trying to find out what is the final temperature of this system. And you can already deduce a little bit about what the final temperature has to be. The final temperature, T final, has to be somewhere in between 100 degrees Celsius and 23 degrees Celsius. So you kind of have an idea of what your correct answer is supposed to be before you even start. Okay, so one thing that we know for sure is the heat lost by the metal is equal to the heat gained by the water, those two Q's that we have there. And we substituted in M times S times delta T for Q on both sides. I like to start by putting the Q up there just so I remember which is the metal side and which is the water side. Now, for the water side, we know it's going to be M times S, and we're going to take delta T and expand it out to T final minus T initial, what we normally use. But remember, over on the metal side, we're going to flip that. And now we're going to have T initial minus T final. So here's the change. That's the difference. From here, it really becomes a plug and chug problem. Get your numbers in and start working through the math. I do like to leave my units out on this type of problem because it gets a little bit cluttered. So we have 25 grams. The specific heat was 0.385. We have T initial, it was 100. We're looking for T final, so I'm going to set it equal to X. For our water, we have 45 grams. Whoops, I said I was going to leave the units out and I put it in. A specific heat. And now we have this T final again, but remember that it's the T final for the system, so the copper and the water are going to be at the same final temperature, so we can make this X as well. And T initial was 23 degrees Celsius. So mathematically, the very first thing you want to do here at this step is to simplify. So I'm just going to put a little note out here. So you remember, what are we going to do with this step right here? We're going to simplify it. And the way I'm going to simplify it is first, on both sides, multiplying the mass and the specific heat together. So I get 9.625, 100 minus X, equals 188.28, and X minus 23.0. So now I've got a little bit simpler. Next, mathematically, what I want to do is distribute. So jot down what I'm doing at this step so you can keep track. We're going to take 9.625 and multiply it by 100, and we get 962.5. And then we'll multiply it by X, and we'll get 9.625X. Same thing over here. We'll have 188.28X minus 4,330.44. So now you can see it's getting a little bit easier to work through. What we need to do next is put our like terms together. So jot a note of what we're doing there. We're working on our like terms. It doesn't really matter. I tend to like to keep everything positive. So in this case, I'm going to add 4,030.44 to both sides. And on this side, I'm going to add 9.625x. I'm going to do that to both sides. I like everything to be positive. They can both end up negative. That's fine as well because the negatives will cancel out. So over on this side, we're going to have 5,292.94 equals 197.905x. Now it's getting really easy to work with. Now we know that we want to solve for x. And so we'll take our 5,292.94 and divide it by 195.905. And that's going to give us 26.7 degrees Celsius for our T final. And if you go back and reflect on this answer, it makes a whole lot of sense. It's falling in between our 100 degrees Celsius and our 23 degrees Celsius. And if you look at the specific heats, it takes a lot of energy to change 1 gram of water by 1 degree Celsius. It has a very large specific heat. So you're not going to get a great temperature change on these particular types of problems. You're going to be looking at small temperature changes. If you will look, whoops, can't quite get it up there. On your separate sheet of paper, I would like you to go to page 284 and try number 42. You're going to find it very similar to this problem. Have this problem right out beside you so you can remember the switch to make with the change in temperature for the metal and each mathematical step you want to make along the way. We have so far everything we've been dealing with. This has been constant pressure calorimetry exposed to the room's air pressure. There is another type of calorimetry, and this is called constant volume calorimetry. Sometimes it's called bomb calorimetry. This is used by a lot of nutritionists. When you see the calories listed on your packages of food, that they have to figure out that in some way, and the way they do that is by using a bomb calorimeter. The energy is measured by an increase in the temperature of a known quantity of water and the calorimeter parts. So they combust that sample of food, and they know how much food is in there, what mass of food it has. And what they can do is measure the energy given off from that sample of food, and that's how they come up with the calories. The volume is constant. No work is done. The pressure does change. Here's the formula for bomb calorimetry. It is the heat equals the change in temperature times the specific heat of the calorimeter, and that's a value that'll have to be given to you. Notice that the constant volume calorimetry equation is different than the constant pressure. In this particular problem, there's no mass, so that doesn't matter in determining the heat. So let's try a sample bomb calorimetry problem. Our sample question, we have 0.5269 grams of octane. You've heard of octane before in gasoline. It's in a bomb calorimeter with a heat capacity of 11.3 kilojoules per degree Celsius. The octane is ignited and the temperature increase is 2.25 degrees Celsius. Calculate the amount of energy released in kilojoules per grams. So let's go to work on our problem. We know we have 0.5269 grams of octane. We had the specific heat of the calorimeter. It was 11.3 kilojoules per degrees Celsius. We know how much the temperature changed by. It changed by 2.25 degrees Celsius. And they want to know what is the Q for this sample. And they gave us a really specific unit. They want to know in kilojoules per grams. Well, let's start just dealing with the Q part first. Let's just get our kilojoules, and from there then we'll add in that gram unit. This is a bomb calorimeter, and with a bomb calorimeter, the energy equals the change in temperature times the specific heat of the calorimeter. So remember, once again, that mass is not involved in this problem. So for our change in temperature, we have 2.25 degrees Celsius. And our specific heat of our calorimeter is 11.3 kilojoules per degrees Celsius. You'll notice our degrees Celsius cancels out and gets us to that kilojoule unit that we're interested in. We'll multiply that together and we get 25.4 kilojoules. Now, something I want you to be careful of is thinking about the sign of this. Remember, we talked about endothermic versus exothermic in the previous online lecture. Do you think this Q should be positive or should this Q be negative? If you answered negative, you are correct, because if you go back and look at the problem, it said the heat was released. And anytime heat is released or the temperature increases, we always want to make sure we put a negative sign on that Q. It's not mathematically there for any reason. It's there to show us which way the heat is flowing. In this particular case, it's exothermic. So now we know the kilojoules. So let's get it to kilojoules per grams. Well, we've got kilojoules and we've got grams. So yep, all we got to do is divide these two numbers. Negative 25.4 kilojoules and 0.5269 grams. We'll divide that and we get negative 48.2 kilojoules per gram. What if you wanted to figure out the moles, if it was kilojoules per mole? Well, now that you know that the kilojoules per gram and you know that it's octane, you could use the molar mass and you could even switch that now to kilojoules per mole as well. Dimensional analysis units will be our friend in this chapter. I have another sample problem for you to try on your separate sheet of paper. Again, back to page 284. Try number 49 and see how that goes. This is the last problem I'm going to work for you in the chapter on an online lecture. What we're going to finish up with is Hess's law. It's not difficult, but it doesn't translate real well to working the problems in the online lecture. I think it'll work better in class. So what I'd like to do is just get our last few slides, get the blanks filled in, and then when you come to class tomorrow, we'll actually work Hess's law and standard heats of formation in class. I think it'll work better for us. So Hess's law, this is once again, Hess's law is another way to calculate enthalpy. And remember, we talked about that enthalpy is a state function. That means the change in enthalpy is independent of the chemical pathway taken. Remember, anytime you can put a triangle in front of something, it's probably going to be a state function. That triangle means we really only care about where did we end up and where did we start. We don't really care about the path in between. Where did we start? Where did we end up? What's the change? A couple things about enthalpy. Because it is a state function and the pathway doesn't matter, enthalpy is the same if the reaction occurs in one step or it takes several steps to get through the problem. If given several steps, you can find the overall reaction and the enthalpy change associated with it. I really like doing these problems. They're kind of like little puzzles to figure out. There are a couple of rules that you want to follow when you're doing Hess's law. The first rule, if a reaction is reversed, so that means if instead of it having going reactants to products, you flip it, so now it's going products to reactants. Well, if you reverse the reaction, then you need to change the sign of delta H as well. If it was positive one way, when you flip it, it's going to be negative the other. Number two, the magnitude of delta H is proportional to the amounts of reactants in products. If the reactions are multiplied, then delta H has to be multiplied as well. And the final rule, when given separate steps, we want to add them together so that you get the overall reaction. Add them together so that you can obtain the overall reaction. So these are kind of like the rules to play the puzzle that is Hess's law. You have to remember, if you reverse a reaction, you reverse the sign. If you multiply a reaction, you multiply delta H. And the last step, add everything together. And let's talk quickly about standard heats of formation. Standard heats of formation, there you'll see tables on page 262, and then there's a really big table on page A21, that's Appendix 21. If you've got those flags at home that we had talked about earlier, having to mark our tables, I'd put a flag on that page because you're going to use that a lot. Here, see delta, we have the change in the standard enthalpy of formation. This is the change in enthalpy that accompanies the formation of, and this is really important, highlight this. Notice I'm putting it in all capital letters. It's for 1 mole, 1 mole, 1 mole of a compound from its elements with all of their substances in standard states. Well, that lends itself to a question: what is a standard state? The first thing you'll see for standard states is you'll see this little degree sign. You see it up here. That means standard state. For a compound, this means that gases are at 1 atmosphere. For a condensed state, we would have a pure liquid or solid. For a solution, this means we're dealing with a 1 molar concentration. For an element, this would be conditions at 1 atmosphere and 25 degrees Celsius. So at these conditions, is it a solid, a liquid or a gas? Let me just move this real quick so we can see that. Here is the equation that we use for this, the change in the enthalpy of formation of the reaction, and then we got this big ugly thing. Delta H equals the products minus the reactants. If you remember that, you can get through this. So that's the key if you're doing standard heats of formation. We will work on this in class tomorrow, so just make sure you get any blanks filled in. And lastly, once again, like I told you before, I'm not gonna do any of these examples for you in the online lecture. They aren't difficult. Don't think that I'm not doing it because it's so hard. But if you do it live, it's just a lot easier for you to do and for us to do together. So that ends our online lecture for today. Please make sure that you bring those couple of problems that you needed to do to class tomorrow, and we will work on problems tomorrow. See you later.